Start now because whoever is late, then. Is the microphone working or?
It's working wonderful. Thank you.
Oh, okay. Today we're going to present some what we do in materials application, and the presenters are myself and Reinhard, and I'm going to talk about the following subjects. The schedule of this presentation, we start with safety moment, which will come shortly, and then introduction, what we do. Secondly, our relation with other departments in the company, and then materials of construction, corrosion types and mechanism, and then we take a break, and material selection, corrosion control, corrosion monitoring, welding manufacturing, non-destructive testing, and what specification we prepare. So we switch then to Reinhard, and he will present painting, coating, installation, refractor, and fireproofing. And then we end at 7:30. The safety moment, this incident happened in 1984 in Chicago, one of the refineries. And this is amine absorber, high pressure amine absorber. And it was built in, it was commissioned in 1970. And from 1970 to 74, they noticed hydrogen blistering in this course of the vessel. And then they decided to replace it. And it was replaced, the section was replaced at that time, and it was put back in service, and they didn't do any heat treatment, just welding it back to other sections. Subsequently, they did several inspections, but didn't notice anything. And in 1984, which about 10 years afterwards, they noticed there is some, there was a little hissing leak, and they tried to approach the vessel, and soon after, this top section just propelled and flew about 1 kilometer, 0.6 miles from that spot, and 17 people were killed because of this incident. Investigation of this incident indicated that cracking had happened adjacent to the welding that was done, and it was very hard welds, and cause of failures assumed to be or determined to be hydrogen-induced cracking. And this was created a lot of scare all over the world, and the refineries generated a lot of attention to this mechanism of corrosion and what to do about it. And since then, a lot of development knowledge had happened that helped industry to avoid such incident. But the main point of this safety moment, that had this was done properly, if they knew that, wouldn't happen, this incident wouldn't happen. And these 17 people were not killed. So this is the main point of this presentation, of this safety moment. Next item. Okay. What we do in our group is we do material selection, corrosion prevention and monitoring with different methods I'm going to talk about. We do welding control on specifications, and manufacturing, that we deal with vendors on their problems, try to solve it. We specify non-destructive testing as needed for prevention of incident of corrosion and damage. And then also we get involved in coatings, insulation, refractor, fireproofing, providing specifications and handling all these issues with the project. Of course, we prepare specifications if needed. Otherwise, we use normally client specification for those items. Our location, we are in the mechanical group, which is part of engineering. Okay, sorry. We are part of the engineering, which is part of operations support, which is part of the big boss. And then in the mechanical engineering, we are part of materials application here. We deal almost with everybody in the department, with all the mechanical engineering disciplines. We check their data sheets for material requirements and insulation, coatings. We get from process people the information we need to develop material selection. We deal with piping, instrument, structural engineering, reviewing their welding documents and dealing with their material selection. We deal with project management, giving them our deliverables and progress. Also with project control, we do the progress and updates on that. We deal with quality control department. Whenever they have an NCR or a problem in materials fabrication, they refer it to us so we can review it and give them our opinion how to get around it. And then we deal with document control. They provide us with all the documents to review, and we give it back to them. And we deal with procurement. They go out, they buy equipment. There's a lot of requirements, and we check if they have questions, they come back to us. We deal with the construction sites where they have problems with the fabrication, problems of using wrong material, welding problems. They come back and ask us. We help Martinez office with Shell Martinez, Tesoro, Wilmington, Long Beach, and Houston, Reading, and Calgary offices. Also, sometimes we deal with the London office for our need basis. Materials of construction used in oil and gas industry as well as in chemical industry are listed in this slide. And of course, it is carbon steel is a predominant material. I'm attaching here a graph which explains what this carbon steel is. Carbon steel, it is iron carbon alloy actually, and we are using steel is in this range where it's about 2.3% carbon, and our steels are in this range. If we go in higher content, we have cast iron, which is about in this range. So it is alloy between carbon and iron, and make the steel, which the carbon gives the strength to the iron. What happened here? It's not okay. So we have. I'm not going to go over all these items, but we have alloys which give strength and resistance to hydrogen corrosion. We have another alloys which more chrome, which gives resistance to sulfide corrosion. Of course, stainless steels, different grades and different applications. And then we use duplex, which came. There's two types of duplex: regular duplex and super duplex. They have advantages of being resistant to sulfide hydrogen chloride cracking, and they are cheaper because they don't have as much nickel as the stainless steels. But they are limited to only 600 degrees F. You cannot use them because afterwards they become brittle, so you cannot use them above 600. But they are giving advantage in where you have a chloride environment. Ferritic steels is used in, it is predominantly 12% chromium or 17 chromium. It's used for trays and maybe some parts of the rotating equipment, and also there is a martensitic chrome steels which has a higher carbon content. It's not easy to weld, but it is good for high strength properties. We use also nickel alloys for high temperature applications, very corrosive applications. These cast alloys is used also for corrosion resistance of different in pumps, and where you have high, for example, sour water service or sulfuric acid type service. Heat resistant casting is used in reformer heaters and steam reformers, or ammonia plants, ethylene plants. This one is used. Copper alloy is used predominantly in seawater type service, heat exchangers, coolers, condensers, and also for some brass is used in some coolers. Titanium alloys is very resistant to corrosion and used in a lot in refineries and sour water type systems. There are different grades, and basically it's almost 100% titanium with a little bit of alloying elements like palladium. Zirconium is very expensive material, rarely used in refineries or petrochemical, but this is one option we have. We also specify non-metals, which is like PVC, all kinds of Teflon, Kynar, and then rubbers, elastomers, It is used in equipment, for lighting, sometimes for pipes. You can use non-metallic pipes. We went through this one. Types of corrosion. The regular type is a chemical, which is direct chemical reaction between metal and the environment. An example is oxidation, where the oxygen oxides like iron or carbon steel, and sulfidation by reaction of sulfur or hydrogen sulfide with the steel. It is direct reaction. It is just like chemical reaction. The other other mechanism is electrochemical corrosion. The electrochemical corrosion, it is a reaction between the environment and the steel or the metal, but it occurs in two sides. The metal goes into solution, becomes ionic, and it leaves on the metal surface, it hits ions. The ions goes through a metal conductor to the cathode, where it neutralizes hydrogen or oxygen, and this is a circuit of reaction, continuous like that. So the metal is always corroding, actually going to solution, and its electrons complete the circuits of corrosion, and this is, they call it electrochemical reaction. The very common mechanism of corrosion in the refinery, there are lots of them, and we have to be aware of them, because otherwise we make improper material selection. And the first one, I'm just putting them alphabetically, not in order of importance. The amine corrosion, it is very critical in amine units, which we are involved too much. The ammonium bisulfide corrosion, it is in hydrotreaters, hydrocrackers. Ammonium chloride corrosion also in hydrotreaters and reformers. Atmospheric corrosion, it is all around, especially is critical in nearby oceans and sea fronts. Boiler feed water and condensate corrosion is a problem too in a boiler plant. Carburization in reformer heaters. Caustic corrosion, if you use caustic at high temperature, relatively high temperature, not very high. CO2 corrosion is very important in jobs we do in Alaska. For the North Slope, it is a predominant corrosion mechanism that we have to take care of. Cooling water corrosion, cooling water, if it is not treated properly, it can cause severe corrosion. Corrosion under insulation, because insulation can trap some water behind, and the corrosion will happen under the insulation, nobody notices it, and you end up with some severe corrosion and leaks and maybe disasters. Erosion corrosion, if you have stream velocity and corrosion at the same time, it can accelerate the corrosion mechanism, and they call it erosion corrosion. Flue gas dew point corrosion, if you are burning in a heater flue gas or oil which has a lot of sulfur, and to produce SO2 in the gas, and then this SO2 forms some sulfuric acid or sulfuric acid, and it condenses in the tail end of the furnace, in the cold end, and cause corrosion in the convection section of the furnace. Fuel ash corrosion, if you have vanadium or sodium in fuel oil that you burn in the heater, this ash, this deposit on the heater tubes and cause damage to the tubes. Galvanic corrosion, what happens between you have two metals of differential potential, and then the less noble material will corrode. I will explain later. Graphitic corrosion of cast iron, where the graphite it is cathodic relative to the iron, so the iron nearby corrodes, and you end up leaving only graphite, and iron disappears. So the cast iron dissolves actually. High temperature corrosion by hydrogen sulfide. This is very common in hydrotreaters, hydrocrackers. High temperature hydrogen attack, it is when you have high temperature hydrogen at high partial pressure, hydrogen can react with the carbon in the steel and can cause cracking of the material. Hydrochloric acid, of course, HCl is very corrosive acid and can corrode. The same for hydrofluoric acid. And then metal dusting, it is something you don't see except in hydrogen reformers and ammonia plants, which attack. It is some kind of carburization, but it's a different, slightly different mechanism. Microbial corrosion, microbes in cooling water can cause corrosion because they make colony and they produce some acid under the colony, and that colony, the acid formed by the microbes corrode the metal. Naphthenic acid, some crude, they have naphthenic acid in them, especially in California and some Far East crudes, I think maybe Venezuelan crudes. And this naphthenic acid has characteristic of severe corrosion of metal, especially in the vacuum section of crude units. Night riding, this is also a phenomenon in ammonia plants where you have a lot of nitrogen at high temperature, and nitrogen react with the steel and produce nitrides, which make the metal very brittle. Oxidation, of course, high temperature corrosion by oxygen. Soil salt corrosion, it is in underground structures. Sour water corrosion, all where we have sour water can have corrosion. Sulfidation, we have hydrogen sulfide at high temperature cause corrosion. Sulfuric acid, of course, cause a lot of corrosion. This, and I give you examples of what like photos of some result of, this is a result of naphthenic acid corrosion. You can see the corrosion here. And this is a result of carburization. We see the furnace tube, which has the carbon diffuses in the metal and make it iron carbides. Actually, you lose the metal that holds the pressure, and then actually eventually you have only iron carbide in here, and that actually is no good. And this is wet CO2 corrosion, where it is very characteristic. You have deep, sharp pittings, and this is what happens if you have wet CO2 corrosion. This is under insulation, under insulation corrosion. And see what happened under the insulation. This is erosion corrosion, where you see the effect of flow, where the flow impinges on the metal, so it accelerates the corrosion, and that's why they call it corrosion erosion. If you have a weld, also it is like an obstruction in the flow, so it makes localized corrosion here. This is the ash corrosion, which is from fuel oil that you burn in a heater, and it forms like something like ceramic type, but it attacks the metal, and the metal gets lost. This is the example of galvanic corrosion. If you have a noble metal next to non-noble metal, because of the galvanic action between these two metals, the least noble metal will corrode, and this is an example of what happened here. This is the galvanic series, where the metals on the top that are more active, they are anodic, and this is and less and more noble metals are at the bottom. For example, gold, platinum, all graphite, they are more noble metals. Zinc, aluminum, magnesium, they are less noble. If you combine this with that, this one will corrode and sacrifice for this one. The steel is somewhere here, still not very resistant. This presentation is available in the iDrive, and if the handouts are not very clear, you can download from the iDrive or make prints there, which is this prematurely, this slide came in, but this is an example of high temperature corrosion attack. And here the hydrogen, high temperature hydrogen react with the iron carbides in the steel and form methane inside the metal and leaves iron without carbon. And as the pressure builds up inside the crystal, it starts breaking, and you see the fissures inside the metal. This is what they call it, hydrogen attack. This is, again, hydrogen attack is a structure before, no, this is a regular structure, but you can see the fissures here from hydrogen attack, and eventually it shatters and breaks out. This is hydrofluoric acid corrosion. Hydrofluoric is very, attacks certain metals vigorously, and if you have copper, nickel, chrome, it attacks, and this, by instance, carbon steel has some of these alloys inside, so hydrofluoric acid attacked this part. This one didn't have this impurities, so it didn't attack it. microbial corrosion, and under a colony of microbe colony, you have this acid formed or some aggressive compound forms and cause localized corrosion. And alloy, some microbes, they like to eat nickel, and corrosion starts from inside, and you end up with pinhole, and this is like a stainless steel tube in heat exchanger. So you end up with holes, and the rest of the pipe is sound, but where the colony was there, the corrosion. This is corrosion by naphthenic acid. Naphthenic acid, it forms some very loose corrosion product, and if you have a flow, impingement or flow, it goes very fast, and this is typical for naphthenic acid corrosion enhanced by stream flow. The naphthenic corrosion resistance is just, I found this interesting. It is naphthenic acid corrosion resistance is by molybdenum content. The more molybdenum, the more the material is resistant. And of course, these are not resistant at all. It's a very small amount of molybdenum. These materials, they don't have moly, very little here, and these, they don't have moly. And then you start getting resistant by 316. And then 316 has between 2 and 3% moly. 317, it has 3 to 4% moly. So these are the materials normally used for naphthenic acid corrosion, and predominantly we are using now 317 because it has the new material 316 has moly close to 2%, which was no good. So we try to use 317 nowadays. Of course, there are 6 moly steels, and these alloys have a lot of moly, so they are very resistant to naphthenic acid. Example of oxidation, which is obvious, probably you have seen that. This is an example of a hole resulted from in a stream where you have sulfidation inside. Here it was like tubes where you have a sulfuric acid, and there's a crevice between the baffle and the tube. The corrosion occurred in this location. Am I speaking so fast, or it is okay? Slow down? Okay. Because we have a lot of material to present, and I'm afraid that... okay. Types of corrosion, cracking. The ones I mentioned before, they were mostly corrosion metal loss type. But here we're talking about cracking. And we have, as I mentioned before, we have mean stress corrosion cracking, which happens for carbon steel at certain temperature if you don't hit stress relief. Ammonia also creates stress corrosion cracking for copper alloys. So we never use copper alloy if you have a stream has ammonia in it. We cannot use it, otherwise it will crack. Carbonate cracking is also, we have a high carbonate content at high temperatures and high pH. The carbonate ion can cause stress corrosion cracking. Caustic can also cause stress corrosion cracking for carbon steel if it is not stress relief. Chloride cracking, of course, with stainless steel, which is I showed you. I'll show you some figures. Corrosion fatigue, if you have fatigue environment and corrosive environment, it causes corrosion fatigue. High temperature hydrogen attack, which you have seen a few minutes ago. Hydrogen embrittlement. This hydrogen, as it diffuses at high temperature inside the metal, it gets trapped inside the metal, and the metal loses ductility, becomes brittle. So unless they call it outgas the hydrogen from the steel before you shut down, because when it is hot, the equipment, hydrogen is inside the metal. If you cool fast and you don't get rid of the hydrogen traps inside the metal and can crack the steel. So there are operational procedures that you have to outgas before you cool down to avoid, or cool down slowly at high temperatures, so you get rid of the hydrogen from the metal. Liquid metal embrittlement. You never use, we try to avoid use of galvanized material next to hot type surfaces, because molten zinc, because zinc is very low melting material. Once it goes on, for example, on top of carbon steel, it will crack it right away. they call it liquid metal embrittlement. Polyethylenic stress corrosion cracking, it is a mechanism that affects stainless steels and ink alloys, and it is due to carbide precipitation, and when I go to the slide, I'll explain how it happens. Titanium also, if you have hydrogen environment due to corrosion, hydrogen diffuses in the titanium and causes a lot of embrittlement. Wet H2S cracking, it is the same as example is the how we call it, the safety moment. It is actually one of the mechanisms I mentioned here. They have wet H2 corrosion can cause blistering, sulfide stress cracking, hydrogen-induced cracking, stress-oriented hydrogen-induced cracking. Some examples, this is a mean crack next to a weld, and it is predominantly intergranular. If you have this structure, you have the intergranular crack. This is a ammonia crack in a copper alloy. You see it is almost intergranular, sometimes it is transgranular. Carbonate cracking, again, it looks like intergranular type cracking. This caustic cracking, it looks like in a boiler or somewhere. You have the tubes rolled in, have high stress, and you have caustic entrapment here, and it cracks carbon steel, as you can see. This is another example of caustic cracking. This is the stress corrosion cracking by colorides, and it is typical. If you see branched crack like that, it's 100% due to coloride cracking. And you see how it is transgranular. There is a theory, if your temperature below 140, chloride cracking is a function of concentration of chlorides and temperature. And they found in some cases, if you are below 140, stress corrosion cracking will not happen irrespective of the temperature. But you always don't take this for granted. You have to analyze what is in the environment. You have to be careful to apply this blindly. Liquid metal embrittlement, this is an example where I think galvanized metal come in and attack the carbon steel and stainless steel and cracks it all the way. Polyethylenic corrosion cracking, it is a phenomena where in stainless steel it is made of alloy when it has some carbon, and carbon diffuses into the grain boundaries and form chromium carbides. And if you have rich in chromium carbides and you have adjacent areas less in chromium, you have a galvanic cell here. And if the conditions are wet during shutdown time, corrosion occurs at the grain boundaries. And in case of thermal stress, there is no bond anymore, so it cracks around the grain boundaries. This is another example of polyethylenic. The sulfide, the types of wet H2S cracking. This is the first one is blistering. You can have the hydrogen from corrosion diffuses into metal and accumulates and causes blistering of the surface. So this is one area of accumulation of hydrogen, one area of accumulation of hydrogen, and it interconnects this way, and this is they call it hydrogen-induced cracking. This one is blistering. You can see the blisters here, and it doesn't show cracking, but only blistering here. Hydrogen also, sulfides and from the H2S can cause sulfide stress corrosion cracking. This is the function of the hardness of the steel. That's why we always recommend to have maximum 200 Brinell, and we require to stress leave carbon steel to avoid having high stresses and hardnesses, to avoid this mechanism of sulfide stress corrosion cracking. There's another way, here is another sulfide stress corrosion cracking in the heat affected zone. This is a stepwise cracking and the hydrogen-induced cracking where cracks and occur in the metal. And if the cracks propagate perpendicularly, this way they call it SOHIC, stress-oriented stress-oriented hydrogen-induced cracking. This example of sulfide cracking and stress-oriented hydrogen cracking. And the techniques now to find out such mechanism and shutdowns use wet fluorescent magnetic particle testing, and which can very sensitive and can find cracks in the heat-affected zone of wells. Titanium hydriding, it causes hydrogen goes into the metal and makes it brittle, and you end up with a crack all the way in a tube, and this is how it looks in the microstructure. There are other methods of mechanism of damage and causing failure, like cavitation, which we see in pumps, control valves. If you have vacuum, what happens?